This conference will now be recorded.
So very good evening, students. Today we'll be discussing about the application part of junction transistor or bipolar junction transistor BJT. Mainly there are three uses. One is transistor can be used as switch, transistor can be used as an amplifier, and transistor can be used as an oscillator also, feedback oscillator. Okay, so this oscillator part we will learn in the next class. Today we'll see how transistor can be used as a switch and as an amplifier. Okay, so let us start with the switch action. So this is the circuit diagram. This circuit diagram is called base biased transistor in CE configuration. CE configuration means common emitter. C for common and E for emitter configuration. That means when the emitter is grounded and that has been used in both input and output biasing. Okay. All right. So what is this junction then? This is called BE junction and this is called CE junction. CE junction. Okay. All right. So these are the things we had already learned, how to bias input and output. And in the previous class we had discussed transistor characteristics. In the characteristics we have seen input characteristics and output characteristics. Basically in the output characteristics we have learned three terms. The transistor can act in active region. Okay, its action can be in active region, or its action can be saturation region, in the saturation region, or in the cut off region. Cut off region. So there are three regions of transistor action, or in other words I'll say transistor act in three distinct regions. But then how do you define these regions? These regions can be defined according to the nature of the input and output biasing. Okay, that we had somewhat discussed. Today also we'll be requiring this active saturation cut of these things, so I'll be discussing that also today. Let me uh, tell you first, if you want to use transistor as a switch, transistor has to be always acting either in the cutoff region or in the active region. So cut off or in the active region. So these are two regions within which the action of the transistor has to be confined. Okay, sometime in the cutoff region, sometime in the saturation region. So these are two regions of action. Okay, so let me tell you about the mathematical derivation part, and then I'll tell you whatever this is. This is called actually transfer characteristics. Okay, before, see, this is actually transfer characteristics means when you plot output voltage or current or any output signal with respect to the variation of its input, then it is called transfer characteristics. It is written here. So let us see, this is called base bias. So why it is called base bias? Because in the base region, see, base, this is the base region, it is actually biased with battery VBB. The current IB is sufficient to drive this into forward bias. Okay, or it is sufficient to make the transistor on. That is why it is called base bias. So base is biased with a battery such that it can turn the transistor on. See, these both the junction, this is called input junction, BE junction, and CE junction is called output junction. So if your input junction is not conducting, then output junction you will not get any output. Okay, so I wanted to mean that if your current IB is 0, then your output current also will be 0. So that you have to understand. So to turn the transistor on, you have to have certain non-zero input current or base current. Okay, so here the base biasing is done in such a way that this base bias current is sufficient to turn the transistor on. That is why it is called base biased transistor. All right, now let us do one thing. Let us see this BE junction. Here if I apply Kirchhoff's law, I hope you remember Kirchhoff's law. Kirchhoff's law. And Kirchhoff's law, which law will be using? KVL, voltage law. For this junction, BE junction, suppose for this junction, or for the input, in fact we will be writing for output also, for input. Okay, so first let us write the Kirchhoff's law for input junction, and then we'll write for output junction also. So you know what is KVL? KVL is saying that the sum over the EMF in a closed loop, if I write that is sum over V I, will be exactly equal to the sum over the drop of voltage drop across various resistance I R. Okay, across various, or IR, I1, R1, whatever. So across various resistance. Okay, so this is actually KVL. We'll be applying this now here for the input junction. So in the input junction, you have only a battery, one battery, that is this one, VBB. So you have the EMF VBB for the battery, and this is equal to, see, there will be voltage drop across this RB. So that is IB into RB. That is the drop across this input resistance RB. This is actually external resistance. Okay, and see, BE junction, you know the PN junction, right? This is a PN junction. This is kind of a PN junction. So we know from the knowledge of diode action that when you apply certain biasing across a PN junction, voltage drop will be there across the junction. So here BE junction, see, look, this is BE junction. So there will be a voltage drop across this junction, that is VBE. So I can write this as VBE. So this is the KVL equation for this input. Now look, I can write the same equation for this junction also. I can what I can write is, I can write VCC, the biasing voltage, is equal to ICRC plus VCE. VCE is what? The voltage across this CE junction. Okay, that is VCE, plus there is a resistance in series with the collector. So ICRC, that is the drop across that RC resistance. So this will be equal to VCC. So, but you know what is the output voltage? Output voltage is not the VCC. Output voltage is VCE. So VCE I'll be writing as VCC minus ICRC. I hope it is understandable for you. Now look, I'll be measuring the voltage, input voltage, and see, in the measuring device it is shown VI. Let me write VBB as VI. VBB as VI. So I'll just remove this VBB and write VI, input voltage. Okay, so input voltage is Vi. Now I can give this name VCE as V output because this is the output voltage. So I can write VO. In place of VCE, I'm writing VO because this is the output voltage, and VBB I have converted into Vi. So this is VCE, and this is actually output voltage. Let me write as V out. Okay. So this is input voltage and this is output voltage. Okay. So now one thing you can see that this input voltage actually will drive the current, this one IB. When the current is IB current is there, and if that is sufficient to start the transistor on or switch the transistor on, then there will be output current also. So if I was saying you that if IB is 0, then in no way you are going to get IC non-zero value. It also will be 0 value. Okay, it also will be 0. Now see, then the output voltage depends on the input current or input biasing voltage. Okay, so look, let me tell you the philosophy first here. What happens? Suppose I turn the battery on. Okay, then input voltage is slowly increased. Input voltage is slowly increased from 0 to 0.1 volt, then 0.2 volt, 0.3 volt, like that. If I go zero point 0.4, 0.6, okay, 0.6. Let me first discuss the input voltage when it is below 0.6. So what happens below 0.6? And see, one thing you have to remember here, this is NPN transistor. NPN transistor. Okay, that means base is P, made of P. So this is actually P. So here you look, it is actually connected to battery in forward bias condition. So this is forward bias condition. Okay, forward bias condition. Okay, at least circuit is showing like that. But whether the transistor input junction is really acting as forward bias, that depends on the input voltage whatever you provide. Okay, so suppose your input voltage is increased from 0. In the beginning, what will happen? Until you reach greater than 0.6, the transistor is not going to conduct. Why? Because we know from input characteristics that there is a certain cutoff voltage. Below that voltage, there will be no current. But after 0.6, for at least for silicon transistor, after 0.6 volt, the current will actually increase very sharply. So this is the input characteristics we have drawn already in the previous class. Okay, this is the input characteristics. Okay, I V, this is V B E. Okay, so V B E. Now see, the input voltage is not greater than 0.6, so this is called cut in voltage. Okay, sometimes people can call as cut-off voltage also. So see, a threshold voltage. This is until and unless the input applied voltage is becoming greater than 0.6 volt, the transistor is not going to conduct. Okay, let me see what happens if the input voltage is something like 0.3. That means transistor is not going to conduct. That means what will happen? See, below 0.6 current IB is 0. So here I can write IB 0. If IB 0, as I said, the transistor is not conducting, so this also will be 0. Okay, so if IC is 0, what will be the output? Look, this output. If IC is 0, then you get the output as the collector biasing voltage, that is VCC. That means you get very high voltage as output, right? Right. So when the transistor is not turning on, you will get a large voltage as output, that is VCC. Now let me increase the value of VBE little further. Maybe it just crossed 0.6. Let me get that value as 0.85 or something like that. So this is just above the 0.6. Okay, so when it is above 0.6, there will be some current. So IB will not be 0. Current also, IB will be gradually increasing now. See, this will increase. IB will increase beyond this cut in voltage. So this is having some non-zero value. Then IC also will have some non-zero value. Therefore, you look the output voltage here, because see, RC anyway some kilo ohm resistance, and this IC, if there is some value of current, then you look the output is actually becoming less than VCC. That means output is decreasing, right? Output is decreasing. Okay, now let me increase the input voltage furthermore. If you increase the input voltage furthermore, then IB will be again more. So suppose input voltage is some 1.5 volt, so it is much greater than 0.6. So your IB will be also increasing gradually. Therefore, your IC also will be increasing. So as IB increases, IC also increases. Then what happens? Gradually you will see that suppose it was earlier C1, now the output voltage is V01. This will be further lower than the previous value, right? It will be further lower because ICRC is getting subtracted from VCC. So when the transistor is conducting and the input current IB increases gradually because of applied input voltage VI, then your IC gradually increases. When IC increases, your output is decreasing. Okay, output is decreasing. So this region, see, at this till this region, when this this output is going to be below 1, until it is becoming below 1, will increase the input voltage. So when it is actually going below 1, then what will happen? Then the output, see this collector, see now in this case the collector emitter junction was at reverse bias, right, at reverse bias. But when this IC increases gradually because of VI increasing, then at one time the output voltage will be below 1, and that time this transistor will be in the saturation region. Okay, so we have seen before VBE, like input voltage before 0.6, transistor was not conducting. That is called cutoff region. Transistor is in the cutoff state. Okay, in the cutoff state you were getting maximum voltage. Okay, now as the transistor is turned on, then your ICRC, this product will be increasing and output will be decreasing gradually. Okay, it will decrease linearly. So at this region, the output junction, that is CE, is reverse bias, and the input junction VBE, this will be in the forward bias condition or forward biased. Therefore it will be acting in the active region. So active region means what? Input junction will be in the forward bias and output junction will be in the reverse bias condition. Then it is called that it is acting in the active region, and the active region, the voltage, output voltage gradually decreases or linearly decreases. Okay, and if the output voltage is becoming much lesser than 1 or lesser than 1, then the biasing of this output voltage will become reverse bias to, sorry, it will go, see, it is still in the forward bias, so this also will become forward biased. Okay, this also will become forward biased. So when it is forward biased, both junctions are forward biased, then it is called, it is like the transistor is said to be in saturation region. Okay, so at some time we'll see in the saturation region we'll get nearly zero, like we'll get nearly zero output voltage. So in the cutoff region we are getting high voltage as large as VCC, and in the saturation region we got voltage as low as zero. So see, the output versus input voltage is actually drawn in this curve. This is called transfer characteristics. So as I said, in the cutoff region, transistor was not conducting, and then IB was 0, so IC was 0. The output was maximum, that was VCC. Okay, look this region, this is VCC. Okay, this is VCC. Okay, now as the input biasing voltage increases, it does start conducting. That means IB will be some non-zero value. If IB is non-zero value, then IC also will be non-zero value. Therefore, your output voltage will decrease linearly until it is becoming less than 1. See, this region, from this to this region, almost here. See, this is called active region because your output junction or CE junction is at reverse bias condition, and BE junction is at the forward bias condition. So this is the active region where we can see the output voltage linearly decreasing. So this linear part is called active region, and transistor is transistor has to be operated in this active region when we want to use the transistor as an amplifier. Okay, amplifier. We'll discuss this part later. Let me concentrate on this breakdown, sorry, this cutoff region and saturation region. So in the cutoff region you get maximum voltage, and in the saturation region you get minimum or as low as zero voltage. Okay, so that is what we have seen. So look, if we somehow confine the action of the transistor either in cutoff region or in the saturation region, then it can act as a switch. Right? So what we can do is, see, we have cutoff region maximum voltage VCC, right? And in the saturation region we have output voltage as low as zero. Okay, as low as zero. So we can define the low and high state or off and on stage, like, see, below certain value of voltage in the cutoff region, if we define that as on state, sorry, yes, on state, and sorry, this is saturation, just below, sorry, just above certain level in the saturation region we can use as high level. Okay, on, when the current, actually the voltage is almost zero, just above the zero level. Okay, or below that it is actually cut off, when you don't get any, sorry, you get actually maximum, in the cut off region you get maximum voltage. So below certain maximum value or below, I would say, uh, above certain value of the output. Okay, you can define as on stage. This can be stated as on over here, and off stage okay, anyway, so you can use this alternatively, like you can use the cutoff region as on stage or this as saturation region as off stage. Okay, then after defining certain value of voltage depending on your circuit, you will get certain v certain voltage input and like corresponding to input voltage, some certain output voltage you get. So in the cutoff region, if you confine that as on stage or off stage, whatever you can do, or similarly saturation region you can use as on or off. Okay, so let me define this as on stage when the output is maximum, and let me define this as off stage when the output is minimum. So somehow we have to make the circuit in such a way that the IP is such that it will drive always the transistor either into the cutoff region or into the saturation region. Then only we can use this as a switch. Okay, so this is what is the switch action. Now I'll request you to read the ncert textbook, and if you have further doubts you can ask me like how to use a transistor as a switch. That part is over now. Now we'll see transistor can be used as an amplifier. Okay, so here itself what we have seen that vi, okay, vi or vbb is equal to, let me go to the circuit itself. Look here, so vi or vbb is equal to vbe plus ibrb, right? Similarly, we have VCE or V output is equal to VCC minus IC into RC. Okay. If I take small change in the input, then see, if I take small change in the input, then this VBE, delta VBE plus delta IB, anyway RB is not going to change. This is what you get. Look here, delta VB, this is actually a cut-in voltage. So that is almost fixed. So this is not going to change. So what you get is delta IB into RB. Okay. Now if we take small change in the output voltage also, delta V0, if you are confusing with this, let me clean it. Delta V output, oh, this subscript is not 0, this is O. I have told by mistake. So this is delta VCC delta IC RC. Okay, so look here, you can see from this that the VCC voltage doesn't change. It doesn't change actually. Okay, it doesn't change. So I can take this as 0. Then what I get is minus delta IC and RC. Okay. Now look, this is the change in the output voltage due to the change in the input voltage. So if I take the ratio of delta VO by delta VI, then what I get, I get minus delta IC into RC divided by delta IB into RB. See this delta IC by delta IB, this is called beta AC, a small signal current gain into RC by, sorry, this will be RC by RB. Okay, this is actually this is actually, this ratio output to input, this ratio is called actually gain. This is called voltage gain or small signal voltage gain, and it is denoted by AV. So what you get is, so AB, I'll just interpret this result little bit. AB, what we get is minus beta AC. That means this is current gain, small signal current gain. This is RC by RO. Okay, look here. There is a minus sign over here. What do you mean by this? Look, in the previous graph, what was the slope of the curve here? Slope is negative. Okay, so this is what is actually denoting that. Okay, so what we have got there? Minus beta AC RC by RB. So this is what we get as small signal voltage gain. This is called small signal voltage gain and denoted by AV. And look here, minus sign is denoting the decreasing slope of the output voltage as you increase the input. Okay, that's why this minus sign. Now beta IC, you know, that is delta IC by IB, delta IB, and this is RC by RB. These are the component, external component resistance. Okay, external resistance. These are nothing to do with the transistor. Okay, so directly. So these are peripheral resistance or circuit elements. So you know, if you know beta AC and this output volt, like this outer resistance itself, you can understand what is called voltage gain, small angle voltage gain. Okay, and this minus sign is denoting that input and output are 180-degree out of phase, just opposite phase, input and output signals. Output signals and input signals okay, input and output signals are 180-degree or pi radian are 180-degree out of phase, out of phase. They are actually in opposite phase. In just simple language, they are input and output are opposite phase, in opposite phase. That's why minus sign is coming over here. So this is what is sometimes asked in your competitive exam. So how are this input and output signal in the amplifier, like what is the phase difference between the input and output voltage for the case of an amplifier? This is out 180-degree out of phase. So they have 180-degree phase difference or pi phase difference between them. Okay, so this is very, very important. And you can see that beta AC is a small angle current gain. It has large value. So when we can see, you can see the gain. This is voltage gain. Voltage gain means what? If you apply very small voltage, you can get some, suppose you apply some 10 volt input voltage, okay, you may get some 15 volt output, or sometime you may give 10 volt, you get some 60 volt output. Okay, so this is V input and this is V output. Okay, so this is called gain. If you apply certain voltage, it will be amplified, because you look here, this ratio is having a value beta into AC, and beta has like very large values, and RC by RB. If we just control this factor, then we can actually control the amplification, magnitude of the amplification, just by external circuit, just by manipulating the resistors in the collector and base junctions. We can actually vary the amplification, magnitude of the amplification. Okay, so I'll clean this portion. Let me discuss the amplification part. First of all, if we want to use this transistor as an amplifier, it has to act in the active region. Active region means what? Or active state. That means what? Input junction forward bias. Input forward bias. I'm writing FB for forward bias. F dot B dot. And output junction. Output is CE junction, right? I told you that. Now output has to be RB, that is reverse bias. Okay. This is the condition for active region. Okay. And you have to use the transistor in the active region while you are trying to use the transistor as an amplifier. Okay. All right. Now look, we know that from the input circuit we had already written VBB equal to VBE plus IBRB, right? This is what we had discussed just few minutes back, IB and RB. Okay. Now we know VCE, that is the output. Okay. And that can be written as, or maybe let me write this as VCC minus ICRC. Okay. Now you can see here that this DC voltage is not going to change anything. So whenever you want to use a transistor as an amplifier, what you have to do, along with this input voltage VBB, you have to always apply certain sinusoidal voltage also. Suppose Vi is the amplitude of that. What I'm saying, you have to superimposed AC on DC signal. Here VBB battery is providing DC signal. Okay, VBB DC signal. But if we want to use this as an amplifier, we have to superimpose AC with DC and then provide or feed to this input circuit base region. Look, I am just writing that the voltage now is somewhat like this. Okay, then you will have change. See, VB in is not going to change. Only change you will have, so you will have this as well. Then what extra you have? You will have extra IB, delta IB, this RB plus small Ri. Input junction has some resistance. So you'll get this equation. You look, this part is not changed. That means your original voltage, due to this, whatever output you get, you will get that. Along with that, one sinusoidally varying current, you will, like, because of sinusoidal signal Vi, superimposed signal, you will have in the input characteristics, you will have the change in the voltage, right, due to change in the voltage due to AC signal. So I can write, if my AC is this one, this corresponds to delta IB plus Ri plus RB. I hope this is clear to you. This change will happen due to this AC signal. Okay. Delta IB RB plus RI. RI is the input junction resistance. This here it is RI. RB is this one, external circuit resistance. Okay, so what I can do this, I can write a small r. So small r into delta IB. So what I get, change in the input voltage I got due to AC signal. Look what I have got. I have got delta, sorry, VI is equal to delta IB into small r I have taken. Okay, small r is actually combination of input resistance of the junction plus RB. This is the one, right? Now I'll see similarly the output voltage. What we know, VCC, this is the battery signal biasing voltage, then it is VCE plus ICRC. So in this case also you will see the change in the output current. Since there is now input voltage different, some sinusoidal voltage is superimposed, so your output also will be superimposed here. Okay, output also will be superimposed. So how do you get the output? So you'll get the output V output. Look here, V output. If I just take the change in the output voltage, V delta CC. Okay, so this will be delta VCE, and this will have 0, and you will have minus delta IC into RC. This is what you will get. So change in the output voltage, you will get, this is actually this one, delta VCE. This is equal to minus delta IC into RC. Okay. So if I write change, this change is actually due to the AC signal. This I'll write as, okay. So let me write B output by delta V output by B delta V input. That will give you, see, if I take the ratio of these these two things, so output you have delta IC by delta IB here, and into RC by small r. Okay, this is beta AC small signal current gain, beta AC into RC by R. Okay, so from here you can see that you are getting uh, you are getting voltage gain. Okay, voltage gain. Okay, let me write in the next. So what is the voltage gain you get? Voltage gain you get AV. This is denoted by AV. So this is given by VO by VI. Okay, so this is minus beta AC into RC by R. So RC I can write as RL also, load resistance. Okay, so this is actually the current gain as I have discussed. Sorry, this is voltage gain, small signal voltage gain, small signal voltage gain, voltage gain. And see, the slope we know V by B out by V input will be in the active region. So this linear part. Okay, regions are non-linear. Okay, even saturation region, before it reaches to saturation region, it is non-linear. So this non-linearity actually says that there is no sharp defined boundary between active and cutoff or active and saturation region. Okay, so all right, so here we have got what is called the voltage gain for the amplifier. So this is actually voltage gain for the amplifier. What we get? We get minus beta beta AC into RL by small r. Okay. So this negative sign actually is indicating that input and output signals are out of 180 degree out of phase. Okay. So now see, we have got voltage gain, voltage gain, that is beta AC, sorry, AV. We have got current gain. Current gain or current gain we have got beta AC. Okay. Then what will be the power gain? Power gain will be AP is equal to beta AC into beta AC into AV. This is how we can find out the power gain, and we can use this amplifier as an transistor as an amplifier. Okay. So I'll stop it here for today. You can read these two accents or applications of bipolar junction transistor, and in the next class we may take few numerical example first before we go to feedback amplifier. We'll solve few numerical problem because this two actions are very important. We'll discuss few numerical as well as conceptual question on this part as a switch and as an amplifier. Then we'll go to the next topic. So then we will meet again on Sunday with this topic, like this amplifier and switch action of the transistor, where I will be discussing few numerical problems with respect to various biasing. Okay. So thank you for your patience. I'll stop it here for today. Bye.